Hello and welcome to our notes on free fall. Free fall is a very specific type of motion, which is why it gets its own topic. So far we've been looking at objects that just kind of have, what we've been telling you what the acceleration is. They're usually moving on tracks or carts or along the ground. Objects that are in free fall move in a very specific way. Here's the definition. An object is in free fall when it is only influenced by gravity. And there's a better definition, but we'll get to that when we start talking about forces. An object is in free fall when it's only influenced by gravity. That's good enough for now. What are objects that are in free fall? Well, very obviously, if you take something and you drop it, that object is in free fall. We're going to neglect air resistance for right now. We'll talk about it when we get down closer to the bottom of this page of notes. So something dropped from rest, but it doesn't just have to be that, okay? So this pen, right now it's not in free fall because gravity is affecting the pen. That's why the pen isn't floating, but also my hand is affecting the pen. However, if I drop the pen, the instant that it's out of my hands, it is in free fall. However, it doesn't just have to be something getting dropped. It could also be something getting thrown or launched or kicked, etc. And I will point out that, so if I were to throw this pen while it's in my hand, okay, that is not in free fall. But the instant that it's out of my hand, it is now in free fall. And notice that it doesn't matter what direction it's moving. If I toss the pen up first, that pen, as soon as it's out of my hand, is in free fall. Free fall does not mean the object is moving towards Earth's surface, okay? The object could be moving up. It could even be stationary. The instant I drop this, the very instant that I let go of the pen, it is not moving yet. But it's still in free fall because gravity at that point is the only thing influencing its motion. Gravity is about to pull it down. One other example of something in free fall, actually satellites in orbit. Now you might be saying, well, hold on a sec. They're just circling the Earth, or they're just sitting up there, past the, way up in the sky. How are they in free fall? Gravity is the only thing affecting their motion. Granted, yeah, they're not falling towards the ground, but again, they don't have to be. Gravity is the only thing affecting their motion, therefore they are in free fall. Now, the reason that we spend a lot of time on free fall is because there's one very important rule with free fall. There's one characteristic. Yes, okay, so objects that are only being influenced by gravity, those are ones in free fall. That has a very important consequence. So this is very important to remember. On Earth, when an object is in free fall, it has a certain acceleration. Every object in free fall accelerates at the same rate, and we will show this and prove this in class. Every object on Earth accelerates at the same rate of 10 meters per second squared. We call this the acceleration due to gravity. You can call it free fall acceleration, you can really call it a whole bunch of different things. But the acceleration due to gravity has the symbol little g, okay, lowercase g, and it's equal to 10 meters per second squared. On your reference tables, it actually says 9.8, but we can get away with using 10. And if you took regents, or people who do take regents, they actually use 9.81. It's fine. They all approximately do the same thing. We're going to use 10 in this class to make the calculation simpler. Okay, but that is a key fact. Every object on Earth that is in free fall accelerates at the same rate. If you go to the moon, there's a different free fall acceleration. There's a different acceleration due to gravity. I think it's about 1.6 meters per second squared. Okay, so different locations have different accelerations due to gravity, but the one that we're predominantly going to use is the one for Earth, where the acceleration due to gravity is 10 meters per second squared. I'm not really worried about you guys doing the math with questions about objects that are in free fall. That's pretty self-explanatory. If you've done the math up to this point with objects that are moving on ramps or along surfaces or whatever, then this is just a special case of motion where the acceleration is a given number and it's always the same. It's 10 meters per second squared. What I'm more interested in is doing a little practice with graphs and how the graph of an object that's in free fall looks if you were to graph it. So here's what we're going to do. we're going to make graphs that show objects that are falling from rest from their origin. Okay, so the origin meaning their graph spot. In this first section, we're going to assume that down is positive. Okay. Oh, and I should point out, acceleration due to gravity is 10 meters per second squared. Since it's acceleration, it's a vector. It needs direction. We're just going to put towards Earth. Okay. Objects accelerate. If they're in free fall, they're accelerating towards Earth. That doesn't mean they're necessarily moving towards the center of Earth, but they are accelerating in that direction. Remember, acceleration is not the same thing as motion. Okay. It's not the same thing as velocity. An object can move away from Earth, but still be accelerating towards it. That would mean it's slowing down. Like if you like when I toss this pen up in the air, it's moving away from Earth, but it's slowing down because its velocity is up, its acceleration points down towards Earth's surface. Technically the center of Earth. Okay, so we're going to say that down is positive, meaning these objects have a positive acceleration as they're being pulled towards the center of Earth. I'm just going to draw in the three graphs that we always draw. Here will be our x versus t graph, v versus t, and a versus t. And we're going to start with the a versus t graph because that's the nice part about free fall. Any object in free fall, as long as it's in free fall, no matter what it is, no matter how long it's in free fall for, if gravity is the only thing influencing its motion, then every object on Earth accelerates at a rate of 10 meters per second squared. And since that's towards the Earth's center, and we're assuming down is positive, that means that in this situation we would have a positive acceleration. Okay? So if we're assuming down is positive and we're making a graph of an object that is in free fall, that's what the acceleration looks like. There's our x-axis, there's the acceleration, a constant 10 meters per second squared. And just based on that, we can figure out what the graphs for the speed and position should look like. And we will practice this and we will demo this in class. For the speed, if the acceleration is 10, remember, acceleration is the slope of a velocity versus time graph. So if the acceleration is positive and constant, then our slope of our v versus t graph should be positive and constant. Perhaps something like this. What this graph shows is that the velocity, if we drop it from rest, makes sense, should start from 0, but the speed or the velocity increases at a constant rate as time goes on because that acceleration is constant. We can go to the x versus t graph because we know that since velocity is the slope of x versus t, and we originally start off with no velocity, and then the velocity becomes more and more positive, that means the slope of our x versus t graph should start off at 0 and become more and more positive. Something approximately like this. Okay. We have a slope that's very low at the beginning, approximately 0, and it gets bigger and bigger to indicate that the object is speeding up. Let's do the same thing, but assume the opposite. Because usually we don't really like to assume that down is positive. People just don't like that. You can do it, it's fine. You can set up your reference frame any way you want. But let's take a look at what the graphs would look like if instead up was positive. We're going to draw the graphs a little differently this time because we're going to have some graphs extending into, or actually all these graphs are going to extend into the negative. If up is positive, that doesn't change anything about the acceleration. It's still a constant acceleration. It's still 10 meters per second squared. But if up is positive, that means going away from Earth, and the acceleration due to gravity is towards Earth. That means our acceleration is now negative. And if the acceleration is constant and negative, then that means the slope on our velocity versus time graph should be constant but negative. And since the object was dropped from rest, starts here, constant negative slope, the velocity is decreasing like this. And since the velocity starts off as 0 and is negative and gets more negative, that means our slope here should start off at 0 and get more and more negative. Probably something about like this. Because remember, the slope of a position versus time graph tells us the velocity. This slope is negative and gets more negative as time goes on. Okay, it starts at 0, same as our velocity. Okay, those are the graphs, and we will verify those in class. Notice that these are just the mirror images of each other. So notice that the changing the reference frame doesn't necessarily change the shape of the graphs. It just changes like their orientation, I guess you could say. Okay, so changing the reference frame just makes you look at them slightly different. I promised that we would talk a little bit about air resistance. This is a topic we'll talk more about when we talk about forces. In a lot of topics this year, we are going to neglect air resistance. As a matter of fact, on the reference tables, it says conventions, okay, something that you can always assume is true unless stated otherwise. Take a look at number 2 here. Assume air resistance is negligible. Negligible means you can ignore it unless otherwise stated. In other words, they have to tell you to pay attention to air resistance, otherwise you can just ignore it, okay? Probably about 5% of all problems will say something like, do not neglect air resistance. You won't get many of them. So how does air resistance affect freefall? Well, air resistance, to put it in very general terms, is a type of friction. And I know we haven't really talked about forces. Friction is a force. But what friction does, as you guys can probably tell, if you slide something across the floor and it comes to a stop because of friction, friction, in a very general sense, resists motion. Air resistance is just a type of friction. It resists motion. Air resistance doesn't really cause things to stop. What instead it does, and this is really all friction, it eventually will cause, if you have an object that falls for long enough, it will cause an object to eventually reach what is called terminal velocity. Terminal velocity is just a fancy phrase that means the object is moving so fast, but the air resistance, the resistance to motion from the air is so great that the object physically can't speed up anymore. Obviously, if you have something fall in a vacuum, which is the absence of any material, even air, if you have something fall in a vacuum chamber, there is no air resistance to overcome because, well, there's no air. What we're going to do is we're going to show how the graphs of motion for an object in free fall change if we factor in air resistance. Here's how we're going to show that. I'm going to draw 2 different traces here. The solid line trace is going to show no air resistance. And the dotted line, or dashed line, or whatever I end up doing, is going to show the object's motion with air resistance. And we're going to assume that down is positive. We're going to go back to the first set of graphs. And again, this is just to give you a brief general overview of air resistance and how it works. Okay, what you can expect to see from a graph with where you have something falling and being affected by air resistance. All right? So, without going into too much detail, we'll do that in forces. The way air resistance works is it's 0 when an object first starts to fall. But the faster the object goes, the more and more air resistance piles up. And the air resistance actually causes it to not accelerate at as high of a rate. When the object has reached terminal velocity, what that means is that air resistance is so big that the object is just not accelerating anymore. It's still being pulled down by gravity, but air resistance is balancing that out. All that acceleration due to gravity that it had, or that it was experiencing, I shouldn't say that it had, you can't have acceleration. All that acceleration due to gravity that it was experiencing is negated essentially by the fact that it's moving through the air at such a high speed and there's a lot of air resistance. The acceleration essentially becomes 0. That's when you hit terminal velocity. You can't speed up anymore because the acceleration of that object is 0. Without air resistance, again, we predicted that the acceleration would be a constant, 10 meters per second squared. Let me just draw in the traces of the other graphs real quick. go. With air resistance, the acceleration will start off, if an object is falling and it's falling through air, and air resistance is not something you can ignore, the acceleration will start off at 10, but the faster it falls and the more air resistance builds up, the acceleration will go down, and will continue to go down until the object reaches terminal velocity. So something maybe like this. Hopefully you can see the dotted line. See how the acceleration changes as the object falls? Okay, as air resistance builds up more and more, the acceleration decreases until it hits 0. Now, how's that going to affect the velocity? Well, we know terminal velocity means the object should eventually kind of stop accelerating. It shouldn't gain any more speed. As that acceleration decreases, remember, acceleration is the slope of a velocity versus time graph. As the acceleration for an object that's experiencing air resistance goes, as the acceleration goes down, the slope of the velocity versus time graph should go down as well. In other words, the object's just not gaining as much speed as it was before. Perhaps something that looks kind of like this. See how that slope kind of tails off, and eventually the velocity levels out because the object has reached terminal velocity. How does that affect the position? Again, velocity is the slope of a position versus time graph. So if you have a slope that is decreasing, if you have a velocity that's decreasing, that means you're not going to have as big of a slope on your velocity versus time graph. It doesn't mean that your position versus time graph. It doesn't mean your position is just going to stop increasing. See, the object doesn't stop. It's still moving. It still has some velocity. We know that because the trace for the velocity is above the x-axis. However, it is true that that velocity is not as high as it would be otherwise, so the slope will not be as big. You will eventually have something that just kind of straightens itself out and moves, and the trace will look like a straight line. So something like this, where the object is just clearly not accelerating as much because you have this nice straight section right here that shows constant velocity. When we do this in class, I will try and point out features that look similar to this so you can get a feel for what this would look like when we see this on the motion sensor. Okay, but there's general pictures of the different graphs for an object in free fall and what air resistance does to those, will do to those graphs. The last little bit on the back, we've actually done something similar to this before. We've looked at, we've looked at kind of the conclusion. We've looked at the proportionalities, the patterns before. But I just want to give some actual numerical experience with an object in free fall. Okay, so we're going to fill out this chart. Let's assume that we have an object that will fall for up to 8 seconds. Okay, so there's nothing below it for a long ways. We're going to assume that acceleration due to gravity is 10 meters per second squared. We're going to assume it falls from rest and it falls from the origin. And we're going to assume that down is positive. So the acceleration due to gravity is, we don't have to put a negative sign in front of that or anything. Since it's falling from rest from the origin, the velocity and distance fallen at time 0 seconds are just 0. And now we're going to move on and we're going to start talking about, we will now start talking about what happens to the velocity as time goes on. Let's start with velocity because that's an easy one. Let's think about what we know. We know that the object is starting from 0 meters. We don't really know the final position, but that's fine. We're looking for the velocity. We know the initial velocity is 0 meters per second. We're looking for the final velocity. We know the acceleration, since down is positive and acceleration due to gravity points down towards Earth's center, is 10 meters per second, and that's positive since it matches up with our reference frame that down is positive. And we also know, let's just do the first second, that time is 1 second. So we know initial position, initial velocity, acceleration, and time. We're trying to find final velocity. Now, I can't use the second two equations because those both require knowing how far the object has moved by the end. I can use the first one, however, v equals v naught plus at. And since v naught is 0, I end up with this, 10 meters per second squared times 1 second. The velocity is, after 1 second, 10 meters per second. Now, you can realize pretty easily that this pattern will continue. I can just keep going. I don't have to say now, oh, now the initial velocity is 10, what happens in another second? I could just go back and say, okay, let's just plug in 2 for this. The initial velocity is still 0. And you'll realize that you eventually get to a pattern where you have this basic equation, v equals a times t, since the initial velocity is gone. And since we know what the acceleration is, 10 meters per second squared, your pattern eventually becomes 10 meters per second squared times t. To find v, take the time, whatever it is, after it started falling, multiply by 10. So after 2 seconds, 20, 3 seconds, 30, and so on and so forth. This is a very easy pattern to follow. Okay? And as a matter of fact, we see the pattern that, okay, after 1 second it's moving at 10 meters per second. After 2 seconds, it's moving at 20 meters per second. Well, look at that. The time doubled, so did the velocity. From 1 to 3 seconds, the time triples, so did the velocity. From, let's say, 4 to 8 seconds, that's a doubling of the time, that's a doubling of the velocity. This is just more proof that for objects in free fall, and more widely, objects that are undergoing constant acceleration, velocity is proportional to time. In other words, if t doubles, v also doubles. Or more specifically, whatever happens to, or more generally I should say, whatever happens to t, v increases by the same factor. And you'll notice also that v increases by the same amount each time. It always increases by 10. So that was really nice and easy. The distance fallen, that's a little bit trickier. How do I find the distance fallen? I think the best way to do this, even if you didn't know the final velocities, that's fine. I think the best way to do this is with this equation, x equals x naught plus v naught t plus a 1/2 at squared. I'm going to squeeze that in over here. Okay, we can see that, good. We know the initial position and initial velocity are 0, so we're reduced down to this. X equals 1/2 a times t, and let's see, a is 10 meters per second squared, and then t is 1 second. We're going to square that. 1/2 times 10 is 5, times 1 is 5, times 1 again is 5. X, after 1 second, is 5 meters. Objects in free fall will fall 5 meters in their first second. We can do the same thing here. We end up with a pattern that goes like this. The general equation, since x naught and v naught are both 0, is x equals 1/2 at squared. And we know what a is, so we could even plug in a number. 1/2 times 10 meters per second squared, t squared. The pattern ends up being x equals 5 t squared. So, if your time is 2 seconds, you square that, you get 4, multiply by 5, you get 20. Now, very clearly here, this pattern is not quite very evident, okay? 0 to 5 and then up to 20. That's a much bigger jump. Let's keep going, though. If the time is 3 seconds, we square that, multiply by 5, you get 45. Okay, interesting. So 0 to 5 to 20 to 45. The distance fallen keeps increasing each time. So that's the beginning of a pattern. I suppose you could say, okay, so from 1 second to 2 seconds, that's a doubling of the time. 5 to 20, that's a quadrupling of distance. Okay. 1 to 3, that's a tripling of time. 5 to 45, that's 9 times as big. So that's interesting. If you double the time, the distance quadruples. If you triple the time, the distance goes up by a factor of 9. Let's see if that pattern keeps working. From 1 to 4, that's a quadrupling of the time. And if we plug in 4 seconds, and we square it, times 5, we get 80. How much bigger? Okay, so 1 second to 4 seconds, that's quadrupling the time. 5 meters fallen to a total of 80 meters fallen. How much bigger is 80 than 5? It's 16 times bigger. So interesting. Double the time, quadruple the distance. Triple the time, 9 times as much distance. Quadruple the time, 16 times as much distance. What's the pattern here? it turns out that whatever the factor changes for the time, whether you double, triple, or quadruple it, whatever number that corresponds to, okay, tripling is like multiplying by 3, quadrupling is multiplying by 4, take that number, square it, and then that is going to be how much bigger your distance fallen is. It works here too. 5, so if we go from 1 second to 5 seconds, that's 5 times as much time. If we square 5, we get 25. We should expect our distance fallen after 5 seconds to be 25 times the distance fallen after 1 second. And that's exactly what we get. We get 125, which, when we divide it by 5, is 25 times bigger. I'm going to fill in the rest of these. You can practice this as well. You can do these calculations for yourself. But we see that it is the distance fallen, which we're just going to call x, is not proportional to t. What actually happens is the distance fallen x is proportional to t squared. In other words, if t doubles, x, in other words, the distance fallen, quadruples. Okay? If you were to graph this, you would get a parabola. This is not something that is a linear graph, okay? Graphing velocity versus time, that's absolutely linear. I mean, go ahead and look at our graphs again, okay? Velocity versus time, v is proportional to t, meaning for whatever factor t increases by, v increases by the same factor. When that happens, you get a straight line. If x is instead proportional to t squared, if t goes up by a little bit, x goes up by a lot. You get a parabolic or a quadratic curve. That's what that means. Okay, so again, all I'm trying to illustrate for you is, we probably didn't have all those. What I'm trying to illustrate for you is this pattern, this very repeatable pattern, and we can use this to solve problems. We can use these facts that we have, these proportionalities, to solve problems quicker so that we don't have to plug in a ton of numbers and do a whole ton of math in order to get the answer, okay? And again, just one last thing I want to point out. Notice that the velocity went up by 10 meters per second for each second that the object was falling. That's the definition of acceleration. There's a reason that the acceleration due to gravity is 10 meters per second squared. Acceleration tells you how much the velocity increases for each second the object has that acceleration. So because the object has an acceleration of, or is experiencing an acceleration of 10 meters per second squared, we should expect the velocity to go up by 10 each second. Okay, that's also really useful if you want to know the speed sometime in between, so like 4.7 seconds. Okay, well, after 4 seconds, it's moving 40 meters per second. After every 1 second, you're adding 10 more meters per second on. If you have 0.7 seconds, then you're adding on 7 more meters per second. The speed at 4.7 seconds should be about 47 meters per second. Unfortunately, the distance fallen doesn't have that same pattern. As nice of a pattern, I should say. But you could also notice that the distance fallen increases for each second. For a second, it fell 5 meters, then 15, then 25, 35, 45, 55, 65, 75 meters. And that makes sense too, because as the velocity goes up, it makes sense that your object is going to travel farther and farther and farther each second. It's not just going to go the same distance every second. Okay? This was all just a little introduction to free fall and a little introduction to how you can use tables like this to find these patterns, okay? This is not just something you can do in the notes. You can literally do this on homework, or if you're really stuck and you don't know how one variable is related to another, you can do things like this and kind of tease out the relationship. It's a really good tool to have and one that you should use. Our next topic is going to be projectile motion, which is our last topic in the kinematics unit. So we'll get to that in the next 2 videos. If you have any questions, please let me know. Bye.